Okay, good morning, everyone. Uh, Welcome to another talk organized by Kerala Theoretical Physics Initiative. And today we have a wonderful speaker with us, Dr. Fazlu Rahman. And before introducing the speaker, let us introduce the platform itself. Kerala Theoretical Physics Initiative is an initiative where we have a collective of PhD scholars, faculty members, and postdocs all across the globe, rooting from Kerala. And we primarily aim to enhance the research and education in theoretical physics, and by organizing talks, colloquiums, seminars, and also training programs for master's student. And this lecture series has been going on for more than 2 years, and this time we have Dr. Fazlu Rahman with us. So let us introduce the speaker. So Fazlu, first of all, as you will all understand shortly, the wonderful speaker, and he is currently working on cosmic microwave background radiation. So let us talk about his academic background. He finished his master's in physics from Cochin University of Science and Technology. Then he joined Indian Institute of Astrophysics, Bangalore, India, for his PhD under the supervision of Prabhavati, where he studied galactic foregrounds of the CMB physics. Then later he joined the Rahman Research Institute as a visiting fellow for a short period, and currently he's at Texas A&M University uh, as a postdoctoral fellow. And he's part of the Simons Observatory and also associated with the Score Kilometer Array. So without further ado, let us begin the talk. And during the talk, I believe the speaker can take few questions. Otherwise, let us resort the question to the end of the talk. Over to you, Fazlu.
Hi everyone. Am I audible, Anush?
Yes, you're audible and the
Okay,
slides
great.
are visible. Thank you.
Great. Hi everyone. Good morning. My name is Fazlu Rahman. First of all, I would like to thank Manoj, my good friend, and Ratul, and many of my friends who are there, who are behind the Kerala Theoretical Physics Initiative. It's a great platform doing a lot of wonderful things related to theoretical physics and physics in general. So I would like to uh, thank the organizers for giving me this chance to talk about cosmic microwave background radiation, which is my topic of research also. So today I won't be explaining a lot about my research, but it will be more of a overview kind of talk of what we know about this background radiation and how much our understanding of universe has improved since we detected this wonderful signal. Okay, so without much delay, I'll just enter to the talk. Okay, yeah. So let's begin with the story. So the story is like this. So there were two astronomers, specifically radio astronomers, named Andrew Penzias and Robert Wilson. So they were working in Bell Laboratory in USA, New Jersey, in USA, and they made one of the best radio telescope of that date. It's a horn antenna which you can see on the right, and then they started observing the sky. So the goal of this telescope, or the aim of this project that they were doing, was to basically look for the radio sources, radio point sources, maybe EGN or maybe extragalactic radio sources at different spatial locations. So this is such a huge antenna. You can see the scale of the human with respect to the size of the antenna. So they started observation around 1960s, and then they found that there is some sort of isotropic noise background of roughly around wavelength 7 centimeter that they are getting. Okay, so they found this, and at the first thing, as astronomers or maybe experimental people, so we first try to get rid of all kinds of contaminations that can bias our results, right? So they initially thought maybe there could be some problem with the calibration of the instrument, or maybe then some noise mitigation strategy is not working fine. So they did everything to get rid of it, but still there was some sort of isotropic noise. And the speciality is that this signal of 7 centimeter is coming from every direction in the sky. So if some sort of astrophysical signal is what we are expecting, then there should be some spatial variability for that, right? So, but this is not the case. So that's why they thought about maybe this is coming from instrumental effect or something. So whatever they did, it was not working. So they even checked the presence of some pigeons which nested inside there. You can see that the telescope is so huge that there were a few pigeons inside them. So the droppings of the pigeons could be resulting in this contamination. So they call it dielectric material, and then the radio signals which is coming can bias it. And they thought all kind of possibilities. They tried to get rid of the pigeons, but unfortunately they were homecoming signals, homecoming pigeons, and at the end, they realized that pigeons are also not going to be the problem. At the same time, in Princeton University, Robert Dickey and his group were looking for some leftover radiation of the order of some 3 Kelvin from hot Big Bang, predicted by George Gamow. So Penzias and Wilson, they were not cosmologists. They were not aware of any of these George Gamow predictions, stuff like that. But they got to know that Robert Dickey, who is a theorist and who they were working on setting up some instrument to look for these leftover radiation. So Penzias and Wilson got to know about this. So he immediately called uh, Robert Dickey to Princeton, informing their results. After the phone call, Dickey told his younger colleagues that, boys, we have been scooped, which means that the signal that George Gamow predicted and that Robert Dickey was and their collaborators were looking for was already detected by Penzias and Wilson unknowingly. So science is like this. There can be some unexpected surprises that nature gives. So they got something like that. Now we need to understand what exactly is this signal. So before going to that, so they did a wonderful job. So the excess measurement that the Penzias and Wilson they made, it is now coming from some cosmological sources. So they were not aware of it. So they just wrote a paper in Astrophysical Journal saying that they found some measurement of excess antenna temperature with this title you can see on the top. And in the same journal, in the same issue, there was another article by the Robert Dickey and team explaining the black body radiation. And then, and you can see that on the right side, you can see there is a sentence saying that while we have not obtained results with our instrument, we recently learned that Penzias and Wilson of the Bell laboratories have discovered or observed background radiation of this wavelength. So in this way, in the same journal, both groups wrote articles and they confirm that whatever they have got is the micro background radiation predicted by Gamow, and that is the first light in the universe. So I'll briefly explain what exactly it means in a few slides. So they got the cosmic micro background, and definitely that gave them the 1978 Physics Nobel Prize. So that's it. Now we want to understand what is this cosmic micro background radiation. So to explain that, we have to go a little backward in time. We have to understand the Hubble's law. So in 1929, Edwin Hubble, using galaxy observations, found that the universe is expanding. So we all know about it. Universe is expanding. So then he formulated the idea of Hubble's law. So Hubble's law says that all the galaxies are moving away from one another. So what he found is that all the galaxies are moving away from us, but that's not the exact picture. The exact picture is that each of the galaxies in the universe, they're moving away from one another. And then he formulated this Hubble's law, saying that the velocity of the motion of the galaxy is depending on the distance between these galaxies. So the farther the galaxy is from us, which means that the velocity will be higher. So then there is this Hubble's constant, which is basically telling us what is the rate of the expansion. And this is the plot that Hubble made, you can see. So this is from this library. So the Hubble constant will be basically the slope of this plot. So because on the y-axis there is a distance, and in the x-axis it is distance, and in the y-axis it is velocity. So the slope will give us h0. So from this plot, Hubble measured the Hubble constant to be 500 megaparsec, kilometer per second per megaparsec, but that was I mean, it was containing a lot of error because it was long back. But currently, the CMB measurements as well as other supernova measurements, they are giving us a H0 value of around 70 kilometer per second per megaparsec. So this is the story. So universe is expanding. Universe is expanding in the sense that all the galaxies are moving away from one another. Now we need to understand what exactly is mean by the expansion of the universe. So let's think like this. So I have a coordinate system here. So so this is at t equal to t1. Time is at t equal to t1. So I have a coordinate system, maybe x and y. You can say like that. And then I have two galaxies. So one galaxy is at the coordinate 1, 2, then the other galaxy is at the coordinate 5, 4. So there is a separation d1 between them. So definitely we can measure the separation between them. Now what happens when we say the universe is expanding? That means that at a later time, t equal to t2, the separation between these two galaxies, it has increased. The length or the distance between these two galaxies have increased. But if you check the coordinates of the two galaxies, they are exactly the same as the coordinates in the previous time. So you can, in this case also, you can see that the coordinate of this galaxy is 1, 2, and this galaxy is basically 5, 4. Okay, so the coordinates are basically the same, but the separation has increased. So what does it mean? This means that there is no intrinsic motion of the galaxy. However, the the space itself or the coordinate system itself has enlarged or
कल्याण
has increased, so that
है
we are finding that there is some sort of
एक मोटा
separation
यार ना मालूम नहीं पड़ा
increasing because of this. So this is the idea of expansion of the universe. So we should not think like, okay, one galaxy is moving away from us. We are actually feeling like something is moving away from us. So the expansion is in the way that the space between two galaxies is expanding. So that's the thing. So this idea is theoretically supported by general theory of relativity. And in the language of metric tensor and stuff like that, we have FLRW metric, which explains this thing. So this is the quantity which we have to keep in mind. So this is the scale factor. So scale factor tells us like, okay, what is the size of the universe today with respect to yesterday? Or what is the amount of expansion happened at one time with respect to another time? So this is the idea of expansion. So once we understand this idea of expansion, then we can think of like, okay, what exactly mean by expansion? So although this, you must have seen these images in many places, so this is not representing the exact expansion, but since we cannot visualize the 3D expansion in a 4D space time, so it's always easy to bring things to 2D and visualize. So if the curvature of the space time, if the curvature of the spatial part is spherical, then you can think of all the galaxies are like on the surface of a sphere. So what happens is that the expansion means that the separation between, so you can see that the size of the ball or the size of the globe is increasing, and you can see that the separation is actually increasing. So this is a crude way of understanding the expansion, although this is not exactly representing the reality. So that is the thing. So now if we have some expansion like this, then the expansion is not just for the space. Expansion can happen for anything that happens between that travels between this. For example, the light. So if I have some light coming from a distant galaxy, and while the light is traveling towards me, so the universe must be expanding. Now what happens? Because of the expansion, the wavelength of the light will also get stretched. So this is the idea of cosmological redshift. So you can understand this from this image. So you can see that at t equal to maybe t equal to t1. So here this is the emission of some photon, and it has some wavelength. Now when it travels, the universe is expanding. The size has increased. Because of that, what happens? So the wavelength is stretched. So we can see that, and because of the expansion of the universe, anything which is traveling from far away distance, it so including photon, it will get stretched. So because of that, the light will always be redshifted. So the expansion can be tracked actually by looking all these redshift observations. Okay, so the wavelength gets stretched, which is proportional to the scale factor. So that's also important. So if I say that if I'm finding a source which is some photon which is at a source distance of, let's say, redshift is equal to 2, what does that mean? That means that when the light was emitted, the universe was maybe twice or thrice smaller than the size of the universe today. So basically, redshift is actually telling us like what is the size of the universe at the time when the light was emitted. So understanding all these things will help us in tracking what resulted in the cosmic micro background radiation. Okay, so now let's think a little more deeper. So I already told you, like in the early times, universe was very hot and dense. Why is that? That's because right now universe is expanding. Universe is expanding means that the volume is increasing. So if we look backward in time, if we just look backward, we will find that the size of the universe must be smaller. So if the size of the universe is smaller, if the volume is smaller, the volume is smaller means density is higher. And as per the laws of thermodynamics, if the density is high, then the temperature will also be high. So this is actually giving us the feeling that in the early universe was very hot and very dense. So this is the idea of hot Big Bang phase. So in most of the public talks and popular science books, you must have heard of the term Big Bang. And it's mistakenly understood as the singularity or maybe the initial explosion or something like that. But when cosmologists say hot Big Bang, we don't have a definite proof for the so-called singularity or maybe this initial cosmic egg or anything like that, because those are still speculative ideas. But when we refer to hot Big Bang phase, that represents the phase when universe was very hot and very dense. So the idea is that in the very early universe, density was very high. So since its density is very high, the temperature is going to be very high. So as the universe expands, the temperature drops down, density drops down. So this is the whole idea of hot Big Bang cosmology. Okay, so now let's consider a universe which is composed only of protons, electrons, and photons. Okay, so this is just a simple assumption. I mean, there are many very particles in the universe, but if we just consider electrons, protons, and photons, we can think of like, okay, so here you can see so this illustration is basically telling us like what happens if you look backward in time. So this is where I am, or this is where we all are. It's t is equal to t0, which is the current time. But if I look back, so right now I'm just saying that the temperature of the universe is 3 Kelvin. I don't have any proof for that. Please take my words for granted. T is equal to 3 Kelvin. Now, if I look backward in time, what I will see is that the temperature of the universe must increase. So the temperature is always related to the temperature of the photon or the energy of the photon. Okay, so now if I look backward in time or if I move backward in time, I'll find that there will be a time when the temperature of the universe or maybe the energy of the photon is close to or maybe it's equivalent to 13.6 electron volt. So 13.6 electron volt, if you convert that, will roughly convert to some 3000 Kelvin. So what is the speciality of this 13.6 electron volt? 13.6 electron volt is the ionization energy of hydrogen, we all know. So what happens is that if the temperature of the universe is, let's say, maybe 100 electron volt or 200 electron volt, that means that the photons in the universe have around 100 electron volt energy. So if the universe is composed of only proton, electron, and photon, every time if a proton comes and comes close to electron, they will try to combine, right? But if there is a photon which is having, let's say, 100 electron volt energy, so immediately the hydrogen atom is formed, this photon will attack and ionize the hydrogen atom formed, which means that if the temperature of the universe or maybe the energy of the photon is above 13.6, which is from t equal to 0 to t equal to tr, there is no neutral atom formed. The system is always in ionized state. But if the moment when the energy of the photon drops below 13.6 electron volt, we'll find that the atom gets formed. Because the formation of atom can happen anytime, but the only culprit or only problematic person in this system is photon. So when, because of the expansion of the universe, when the energy of the photon falls below maybe 13.6 electron volt, we will find that the photon has no energy. Photon became weak to attack the newly formed hydrogen atom. So then we will find that in all these epochs, like after t equal to tr, we will find that photons are free and atoms are free, because a photon doesn't have the energy to attack the atoms. So atoms are kept neutral after that and photons are free. So which means that until this time, since the beginning, until this time, everything was in a soup of plasma. Everything was interacting, protons, electrons, photons, everything. It was kind of a very hot plasma. But at the time when t is equal to tr happens, then the universe become neutral, hydrogen atom is formed, and then the photons become free. So this photon is the CMB photon that we are talking about. So this is the epoch of reionization. So this is the time when the energy of the photon comes roughly below 13.6. So this is a very rough sketch to explain the recombination process. So when we do the actual calculation, it won't be exactly 13.6 electron volt. I need to warn you all these things. Also, it won't be an instantaneous process. There will always be a thickness for the this recombination process. Also, there are a lot of other factors. Since I have already told you, we only considered proton, electron, and photons, but there can be other particles, there can be neutrinos, there is dark matters, all these effects are there. But in a very simple picture, this is the easy way to understand recombination and the emission of CMB. So now what happens is that at this surface, CMB is emitted. And before this surface, CMB was busy attacking electrons and protons and stopping them from forming the hydrogen atom. So now, what happens? So, only when the photons are free and when the photons are traveling towards us, we will see them. If they are busy attacking other things, which is basically the interaction, which we always see in fog and all, right? We cannot see anything which is behind fog because the photons or the light coming behind the fog is not able to reach us because of the fog in between. So that means that this region is completely opaque in electromagnetic waves, and CMB is the first light that we will get, and that light itself we will get only after this T is equal to TR. I haven't told this number yet. So this T is equal to TR, we can calculate it, and that corresponds to roughly 3,80,000 years. Okay, so this is around 4 lakh years. So this 4 lakh years is since the Big Bang starting time, if there is something like that. So that is still a speculative thing, but if there is some sort of starting for the universe, then we can say that then after 3 lakh years, we have this recombination phase. But now we also know that this T equal to T0 is roughly 13.8, 13.7 or 13.8 billion years. So compared to that value, this is very, very, very small. So which means that this is immediately after the initial phase of the universe. So now we also call this surface. So this is the surface beyond which we cannot see anything, and after which we can see everything. So we call that surface the surface of last scattering, because that is the surface where the electrons and protons scattered with the photons or maybe the CMB photons the last moment, right? So now from here, so at this point we know that the temperature of the CMB is roughly 3000 Kelvin, but right now we have the temperature around 3 Kelvin. So why is that? That is because this happens when the redshift of the universe is roughly 1100. So because of the expansion of the universe, the CMB radiation which was emitted around with the energy 3000 Kelvin, when it travels towards us, it will be redshifted. And this redshift will, and currently because of the distance it has to travel from the last scattering surface towards us, it will be currently around 3 Kelvin. So that's the whole story of CMB. So CMB is the relic radiation from the hot Big Bang phase. So this is the idea. So there is some sort of very high temperature phase, and from that some radiation is emitted, and that radiation is CMB. Now, again, one more visual representation of what I have just told. So we know that CMB is here. We are here 13.7 billion years, and the Big Bang happened here. All other things are there which I haven't told yet. I'll explain in later slides. So what happens is that CMB and last scattering surface is around 3,80,000, which is at 3000 Kelvin, and we can see everything after that. So the stars, galaxies, formation, all these things happen at this phase, and we cannot see anything beyond that. This is kind of a mist or maybe a fog beyond which we cannot see anything. But understand, everything is in time. This is not a spatial separation. Of course, it's a spatial separation, but when we are explaining this, you can see that this axis is basically time. So this is basically a background or maybe a wall in time beyond which we cannot see anything. Okay, so this last scattering surface is the limit up to which we can see in electromagnetic waves. But if you can find some gravitational waves coming from maybe the early universe, of course you can find that. So this is the story of CMB, last scattering surface, and the opaque situation before that. Okay, so now we can find very nice analog of this system with the sun. So our sun is such a similar system. So let's make a comparison. So the comparison is like this. We know that in the interior of the sun, it's very high temperature. Very high temperature in the sense that atoms are not stable, electrons, protons, it's a dense plasma, right? And since it's dense plasma, we cannot see the interior of the sun. So whatever we see as the sun is basically the photosphere of the sun. right? We cannot see anything beyond that. So it's opaque because photons are busy interacting with all the plasma, electron, proton, and other charged particle. Apart from that, the radiation coming from the sun, because it's a thermal system, that's a blackbody spectra. Also, in the core of the sun, the temperature is very, very high. It's around 1 million Kelvin. Nucleosynthesis happens. So we can find that there is a lot of similarity between the interior of the sun, which is basically a boundary of the photosphere and things inside that in space. Similar to that, we have a boundary in time, which is the last scattering surface. Now, I already told the first 2 points. The third point we have to test. We haven't, so when we say that, okay, CMB is the leftover radiation coming from, maybe that's the radiation which is like escaping from this hot dense plasma, right? So that should be a black body radiation, like the light radiation, light coming from the sun, right? Apart from that, at the core, nucleosynthesis happens. So the situation which enables the nucleosynthesis is the high temperature, which means that the temperature has to be around a million times a million Kelvin for this fusion reaction should happen, right? So this situation, if it happens in the primordial universe, then nucleosynthesis should happen in the primordial universe. So if you go back to the previous slide, we'll see that so I talked about 3000 Kelvin. So if I go back here further, I will have a time when the temperature will be around maybe 1 million Kelvin. So at that moment, I should expect some sort of nucleosynthesis. Okay. So George Gamow in 1940s and collaborators have studied this light nuclei formation in the early universe. So 1940s, so that was the time when nuclear physics was booming. You know the reason, right? All this war and stuff like that. So George Gamow and collaborators, Alpher, Bethen, and they worked on understanding the primordial nucleosynthesis. They got a lot of nice results. You can see the paper here. So this is the famous alpha, beta, gamma paper. So they predicted that there should be some amount of very limited nuclei formation in the early universe, maybe up to lithium. Also, they predicted the blackbody radiation. So this is the blackbody radiation that Penzias and Wilson discovered. So which was predicted by Gamow, and that was discovered by accidentally. It was discovered by Penzias and Wilson. So now you can understand the importance of what they have got, although they were not aware of any of these developments in theoretical physics. Fine. Now we have to make sure that the signal is a CMB radiation. So to make sure that it's a blackbody radiation, we have to draw the spectra of that. So what Penzias and Wilson, what they have measured is just in the language of spectra, that is just 1 point in the spectra. So that is at so the value in wavelength is 7 centimeter. That will roughly be maybe some 4 gigahertz. That will come around here, maybe here. Yeah. Okay, this is frequency is in 1 centimeter, so you can do the calculation. So what I'm trying to say is that when we plot the spectra, what Penzias and Wilson have got is just 1 point in the spectra. But to get a spectra, we have to have measurements in different frequencies, and then we plot the intensity as a function of different frequency, which was done by the Firas spectrometer on board the COBE satellite. So COBE was the first satellite launched by NASA to learn the CMB radiation in detail. So they have a spectrometer. So this spectrometer measured the blackbody spectra. So the speciality of this spectra is that this is the best ever measured blackbody spectra. We have blackbody spectra from many systems, from stars, from sun, everything. But this is the best spectra in the sense that you can see the fit. So the COBE data is here in red, and blackbody spectra, you can see it's in blue. So they measured this, and then they found that the temperature corresponding to this is T is equal to 2.725 Kelvin, which I will show in the next slide. So they measured the temperature of the universe, which is 2.725 Kelvin. So COBE satellite is here, the schematic representation of this, and the PIs of this satellite, John Mather and George Smoot, they won the Nobel Prize in Physics in 2006. So this is the second Nobel Prize for CMB science. Okay, so this is the confirmation that the signal that we have got, that's a blackbody radiation. Okay, so as per the hot Big Bang model, the temperature of the universe, we measured it using the COBE satellite, that is T0 is 2.725 Kelvin. So what does this mean? This means that the universe has a global temperature. So that temperature is a constant value, which is 2.725 Kelvin. So this is what the Penzias and Wilson also discovered, that when they looked at different parts or different spatial locations, they found one constant number. So that constant number will correspond to this 2.725 Kelvin, right? So in all the CMB talks, you will be seeing a lot of these ellipse shaped images. So I want to, before showing many such images, I want to explain what exactly it means. So this is the full sky, the sky only, but in a particular projection called Molvite projection. So Molvite projection, like any other 2D projection, will help us to visualize 3D things in 2D. For example, you can see the surface of Earth here in Molvite projection. So you can see India here, you can see US here, you can see Europe and Africa here. So this is how we can make a 2D projection of a 3D surface. So you can think of the sky as a sphere, a spherical shell, and now you can do Molvite projection on that. So since Penzias and Wilson and all this global measurement, they got a single number, so this will be a single number. So you can see this color, which is 2.725 Kelvin, right? So CMB, the radiation that they have got is a single number, but that is not the full picture. We know that the universe is not perfectly homogeneous. There are a lot of stars and galaxies in the universe. So the stars and galaxies they are basically the density and density fluctuations. We are not finding the universe to be perfectly same, right? Or one particular direction, I'll have maybe some underdensity, and in some other region, I'll have some overdensity. That will result in stars and galaxies, right? So universe is not perfectly homogeneous. And this inhomogeneity should also be seen in CMB. So what does it mean? That means that although we got a perfect number 2.725, that is not the accurate number. So the accurate number of the CMB temperature T will be the T0, which is the 2.725 plus some delta T. So this delta T will be the one which is responsible for the density fluctuations that we see later, and that resulted in stars and galaxies in the later universe. So you can think like this. So this delta T will be plotted like this. So delta T will be, I mean, from theory, we can calculate how much delta T will come given some model. So we'll see that this delta T will be of the order of 100 micrometer, which is like, so this 2.725 is the same. But if you measure the fourth decimal point, fifth decimal point, and sixth decimal point, then you will find fluctuations. So these numbers, this map is basically, you can see that, I have to hide this. Yeah. Oh, yeah. So you can see that the numbers here, it's of the order 10 to the power minus 5 Kelvin. So up to 10 power minus 3, we did not find any change. But if we go to the higher precision, higher value, we'll find the fluctuations. So these tiny fluctuations are representing the physical processes that happened in the early universe. So if we get a number which is just a constant, then there is nothing interesting in it, right? It's just a number. But if we have these fluctuations, if you have different numbers at different spatial locations, although which is very tiny, these numbers are going to tell us a lot about why these numbers are so in the first place. So there must be some reason before the emission of CMB, maybe before the time of the so-called last scattering surface, that led to these numbers, right? So these tiny fluctuations, when we studied them, we can understand what is the physical mechanism that resulted in these fluctuations. So these red regions are basically the higher numbers, and blue regions are the lower numbers. So these density fluctuations, or these temperature fluctuations, which are the density fluctuations later in the universe that resulted in stars and galaxies, they tell us a lot of information about what happened in the early universe. Okay, so now I think I should show you this image. So this image is again shown in most of the CMB talks and cosmology talks. So this tells us like where we are And when is the CMB emission happened? What happened between CMB and us, and what happened before us? Although I don't agree with this usage of the term the Big Bang, because there is nothing like a explosion happened here, but this is just for artistic impression. Something happened here which we are still trying to understand, but we definitely know there is a phase called recombination when the universe became neutral, and until then it was a hot dense plasma. So after that we have only CMB and hydrogen atom. There were no stars and galaxies, so that's why we call it dark age. So dark age in the sense that we don't have stars and galaxies, because stars and galaxies are the things that brighten the universe, right? So now slowly universe, so in the universe the first astronomical objects like stars and galaxies start to form because of various processes. After this, there is a process called reionization that happens. The hydrogen atom, which were neutral, get ionized because of the radiation, UV radiation coming from the first stars and first galaxies. So that's it. And after that, slowly the reionization completes, and then galaxies will, stars and galaxies will get formed, clusters will form, and finally 4 billion, 8 billion, and we are here. So this is the picture we have. So the first stars and galaxies form roughly around this time, although these are all very hot topic of research in the sense that we don't have much observation. So you must have heard of JWST and Euclid and all those telescopes which are going to revolutionize our understanding in these epochs, because until now we didn't have anything of this kind. So this is the simple picture of what happened since the CMB radiation has emitted. Now let's try to understand how and what way we can use to get these anisotropies. So in 1991, differential microwave radiometer, that's again another payload in the COBE satellite, they made the first all-sky measurement of the CMB anisotropies. So I showed you the theoretical picture here. So this is what I'm expecting. So this is the plot I made today morning. So this is not observation. This is, sorry, this is not observation. This is pure simulation. So I need to get something like this. So COBE has another payload. So this payload measured what we were looking for. So if you remember, Penzias and Wilson and whoever came after that, they were all measuring some constant number. But now you can see that, unfortunately, they did not give the color bar here. So COBE measured the fluctuations. But you have to see that in this case, the resolution is very high, but we don't have that much resolution in COBE because it was 1991. The technology was not that good, but they got something. So that's a good news. After that, WMAP came. So WMAP came in 2001. It was another satellite by NASA. So they further improved the maps in terms of the resolution and sensitivity. So now you can see that if you compare this plot and this plot, so this is around 7 degree. The resolution is 7 degree, and this is roughly 30 arc minute. So yeah, that's the thing. And after this, after 10 years, we got Planck. Planck is the satellite launched by ESA with support from NASA. So they gave the best all sky CMB maps to date, measuring the fluctuations at arc minute resolution. So now you can see the improvement. So this is like the mobile phone camera we have, right? We try to improve the megapixels and try to get better and better images. So in that way, we are trying to improve the resolution and the sensitivity so that we will get better understanding of what happens at different scales. So this is the all scale measurement that we have got, but the story is not complete. We still have a lot of ongoing ground based observatories which are looking for tiny features, which I'll explain in the later slides. So this is the measurement made by Planck. Okay, now the question is like, how do we extract physics from these temperature fluctuations? So I have already told you this map is representing the density fluctuations in the early universe. So if it is a red colored region, that means that there is a higher amount of density contrast, or maybe a aggregation of mass or energy in this region. And if it is blue, that actually represents some sort of void in the system. So that is why we can say that, okay, this is basically representing the density contrast, density fluctuations in the early universe, as well as that resulted in the late universe fluctuations. Okay, now how do we understand it? So what I have just told is this. So delta T is equivalent to delta rho, which is the density contrast. Now using these maps, we need to extract what resulted in this and what can happen to this later. So it's going to tell us what happened before recombination and after recombination. So let's try to see how people do that. So we all know about Fourier transform. So the Fourier transform is very simple. What do we do? We have a function f of x, and we try to decompose it in terms of wavelengths, right? Wavelength modes. So we can decompose it. So in that way, we can try to isolate the information in terms of wavelength, the size of the wavelength, or maybe in terms of scales, I can say, right? So same thing we can do for these temperature maps. So these temperature maps are the maps on the sky. So these are basically the functions on the sky. So if there is a function of the sky, then we cannot use the standard Fourier transform, but we have to use the YLMs. This is the basic quantum mechanics, spherical harmonics. Everybody has done that. So you can see that any function on the sky can be decomposed into spherical harmonics. So in my case, the function I have is delta t. I don't want to scare you with equations, but some preliminary equations are there which I couldn't avoid using. So this delta t can be decomposed into YLMs, and then I can see some ALMs here. So pictorially, whatever I'm saying here can be seen like this. So I have a L equal to 2 mode, which is a quadrupole, and then I have some L equal to 3, L equal to 4, L equal to 20, L equal to 100, whatever. So if I have a very high resolution map, I can maybe go to L equal to 1000. And these days we have very high resolution arc minute resolution maps from CMB, where we go up to maybe a L equal to 3000 to 4000. Okay, so this is the idea, that we are trying to decompose the map into different scales. So what is the need for that? The need is in the sense that the physics that is driving these temperature fluctuations, that is resulting in this temperature fluctuation, is scale dependent. Okay, so these scale dependent features need to be extracted, and for that we are doing this business in Fourier domain. So one useful quantity to study all these fluctuations is the angular power spectrum. Again, there is an equation here. If you don't mind, you can just ignore that. But I'm just trying to say is that we have some fluctuations here, and we are trying to understand these fluctuations in terms of standard deviation. Everybody does that, right? We have a mean and we have a standard deviation. Now, the power spectrum is representing the variance or the standard deviation as a function of scale. Right. So this is basically, we have I mean, of course, we can compute an entire standard deviation, but I can also compute standard deviation for each scales. So that is the meaning of an angular power spectrum. So using this angular power spectrum, so I can compute angular power spectrum for any CMB map or any functions on the sky. So using that, I can study the physics. So I'm not going into the details of how to do that, but I can just give you a brief overview. So here, in red color, you can see the Lambda-CDM model of the universe, which predicts some sort of angular power spectrum. So this is the angular power spectrum which is coming from our theory. So Lambda-CDM is our theory, which is explaining the standard cosmology. Now, from the Planck data, Planck data, I already shown you the map. From the Planck CMB data, I can compute this power spectrum. So this is represented by these blue circles. Now you can see that the data is matching very well. It's having a wonderful fit with the Lambda-CDM model. Okay, now I have a data, I have a model. I can do all sorts of things that we do usually, like Bayesian parameter estimation, maybe some chi-square fitting, parameter finding, all kind of things I can do. And Lambda-CDM definitely will have some amount of parameters. So then I can I can find out the best fit parameters for that. So these best fit parameters will actually tell me the composition of the universe, the age of the universe, the rate of expansion, all sorts of the things that we wanted to know. So Lambda-CDM parameter, so the Lambda-CDM model contains 6 basic parameters and a lot of derived parameters. So now using this idea, using Planck data, we got this plot. So this plot is again very famous. We always say that universe is composed of around 70% of dark energy and around 27% of dark matter. And the ordinary matter, which is what we study in our particle physics classes or maybe chemistry, elements, electron, proton, everything, composed just 5%. So 95% of what we know. So this is the energy budget of the universe. So the total energy is decomposed into dark energy, dark matter, and ordinary matter. So dark matter is something which is like normal matter, but it doesn't have any electromagnetic interaction. But dark energy is more mysterious in the sense that dark energy is driving the accelerated expansion, which we found recently. So recently we found that the current expansion is accelerating. So if there is some acceleration, then there should be something which is pushing outside, right? So dark energy is attributed to be the source of that sort of pushing or acceleration of the universe. So from the data, we find that dark energy contribution is roughly 70%, and dark matter is around 27%. So so overall, 95% of the universe is not known to us. That's sad. Yeah. So the idea is like this: we have a CMB map. From the CMB map, I try to get the power spectrum, which is like this. And from the power spectrum, I try to get the parameters. So these are the 6 basic parameters. So I'm not going to explain most of the parameters because that needs separate lectures. So there is NS. NS is basically controlling the amount of power in the primordial power spectra. H0 is known to all of you because H0 is the rate of expansion. Omega lambda is what we have already seen, which is 0.7. Omega m is the matter density, which is total 30%. Then there are some other parameters which I don't want to. This is again baryon density, and this is cold dark matter density. Yeah. So, and also we have the age of the universe, which we all know. So some of them are derived quantities. So for example, H0 is a derived quantity, age is a derived quantity. So what we are trying to get is use from the data using the power spectrum, we try to do parameter estimation and we get the parameters. So this is how we estimated the Lambda-CDM model of the universe. So another important thing is that since the days of WMAP, we have entered the era of precision cosmology. So if you check these numbers, so these numbers, you can see that we have quoted the error bars here. So these error bars are very, very tiny. You can see that this is of the order of 0.00023. Okay, which means that error is very tiny. That implies that we have very good measurement. So that accuracy of our measurement is actually seen here. You can see the fit. The fit is it's completely overlapping, right? Like the delta is very, very close to 0. So this order is, I don't know, this is very small. So this implies that we have entered the era of precision cosmology, which means that we have already got what we wanted. Now we are trying to improve the quality of the measurement, improve the quality of what we wanted to know. So from here, we have to ask the question, are we happy about Lambda-CDM cosmology? Of course, yes. We go to explain the cosmological observations, including CMB, large-scale structure, galaxies, everything with just a 6-parameter theory. So you can think of like, okay, we have all sorts of modeling for many things, which involves a lot of parameters. But for the entire universe, we only have a 6-parameter theory, and that's working perfectly fine. So we are very happy about it, right? But we are not fully happy in the sense that we still don't know 94% of the universe. We don't know what is dark matter, what is dark energy. We are even not sure whether there is dark energy. There are explanations saying that, okay, it could be something different. Dark matter is sort of convinced by most of the people in the sense that, yeah, there are a lot of scales where dark matter is needed. But of course, there are alternative theories for that. So we still need to understand them. Dark matter we don't have, so definitely they are not part of the standard model particle physics. People say it's primordial black holes or maybe something else, maybe some exotic particles, axions, WIMP. People are searching for that, but so far no improvement, anything observationally. Also, there are a lot of discrepancies. Lambda-CDM is failing in explaining some of these things, and we had to propose something else. So these are this is the status of Lambda-CDM cosmology. Of course, we are happy. We are doing great. In the last 30 to 40 years, we did a lot of great job in understanding the universe, but we still need to understand a lot. We just understood how much we don't know and how much we know, right? So that's cool, but still we need to understand. Fine. Now the big question comes, what is the true cause of these fluctuations? So we have already seen the fluctuations, right? So I told you these fluctuations are the density fluctuations, and these density fluctuations are resulting in the galaxies and stars. Now the question is like, who gave these fluctuations, or what is the cause, or what is the true cause of these fluctuations? The answer is inflation. So inflation is a rapid exponential expansion of the universe for extremely tiny fraction of a second. So you can think of it like, okay, the size of the universe was very small in the beginning. Then the size got expanded 10 to the power 26 times. You can think of that number. 10 power 26 is like 26 zeros after 10, after 1. Right. So 10 to the power 26 times in 10 to the power minus 32 seconds. So this is the idea of inflation. In a very short span of time, the universe is expanded, acceleratingly expanded, and this is driven by a scalar field. So inflation is a very active topic. It was proposed to explain some of the issues with Lambda-CDM cosmology, like why universe is so big, why it's flat, and stuff like that. So inflation is this phase in this plot. So you can see that you can see a jump here, right? So this is a rapid expansion. Then the expansion becomes slower when radiation and matter becomes dominated later. So inflation is there. Now people found that although inflation was proposed to address some other problems, people found that the vacuum fluctuations which happen during the early universe during inflation is responsible for the primordial density fluctuations. So if you have learned quantum mechanics, so in quantum mechanics we have the idea of uncertainty principle, so which means that there is always, so we have this idea of 0 point energy, which means even for a harmonic oscillator in its zeroth energy, in its ground state, we have a non-zero energy in it. So same idea is applicable when we go to quantum field theory. So we have fields, and then we say that even for vacuum there is some amount of energy there, and this tiny fraction of energy comes out in a, I mean, that we can measure that only in a very tiny fraction of time. So that can be illustrated like this. So this is an effect of uncertainty principle. So you can see that things are popping out, and then they're just going down, coming up, going down, coming up. So this is completely a quantum mechanical microscopic effect. This has nothing to do with, so whatever I have explained so far. But when this thing happened during inflation, this is happening everywhere. This is not just a cosmological effect. This is happening everywhere. But during inflation, when this happens, so I told you the epoch of inflation is very tiny fraction. So within that fraction, if there is some amount of quantum fluctuation happens, that will get enlarged because of the accelerated expansion. Okay, now that is what we see as the temperature fluctuations. So this is the idea that, okay, vacuum fluctuations are responsible for the primordial density fluctuations. And these temperature fluctuations that we see in the CMB is responsible for the stars and galaxies that we see today. So this is the prominent idea that inflation is driving vacuum fluctuation, is driving I mean, it's basically, it's seeding the primordial fluctuations, and that will result in what we see as the density fluctuations and temperature fluctuations. Okay, so let's talk about inflation a bit. So we know that there is, I mean, there is this idea of inflation, but if somebody proposes something, we should have some observations to test it, right? So of course, inflation has a lot of predictions. So some of them are like the power spectra should look like something in some certain way. We call it scale invariant power spectra. So if I go back to the power spectra plot, you can see that here there is a flat region. So this flat region is what is the information that is there from inflation. So this is roughly flat. So because of that, we can say that the inflation, I mean, it's basically giving some proof that inflation has happened, but that's not complete. Also, inflation is predicting the flat universe. We are finding that the universe is flat, I mean, with the current data. Also, the distribution of the anisotropies should be Gaussian. So we are also finding that we did not find any deviation from the Gaussian distribution. But there is an important prediction for inflation, which is the odd parity polarization mode, which we call as the B mode. So as I already told, apart from the temperature, we have polarization also for CMB. And the polarization can be decomposed into some E mode and B modes. So E modes are having these kind of patterns. So these you can think of like some parity even patterns. And these are B modes. So B modes are some odd parity patterns. From E and B, you may get confused and think that maybe this is some electromagnetic E and B, but it's not exactly the same. Also, although we can see some sort of similarity between them, but they are not exactly the same. I just warn you. So E modes are detected, but B modes are not detected. B modes are very special in the sense that they are arising due to the primordial tensor perturbations happening in the early universe. So if you have heard of gravitational waves, we know that gravitational waves are coming because of the tensor perturbations in the early tensor perturbations anywhere. So when there is some black hole collapse or anything happens, there will be some tensor fluctuations, and that will result in gravitational wave emission. That's what we are seeing. So if there is tensor perturbations anywhere, we will see gravitational waves. So B modes are coming because of the tensor perturbations in the early universe. But B modes we haven't detected so far. It's very, very difficult to detect in the sense that the amplitude of B mode is of the order of nanokelvin. So if you remember, the global temperature value of CMB is 2.725 Kelvin. So that is what Penzias and Wilson and whoever came after that, they got it, right? After that, we had to wait around 30 years to get the fluctuations. Fluctuations are of microkelvin range, right? Now we are looking for something in nanokelvin. So nanokelvin is even difficult to detect. We haven't detected B mode yet. There were some announcement from some CMB experiments a few years back saying that they have already found it, but later they realized that this is coming from some dust emissions from our own galaxy. So that's another big challenge. Although the B mode coming from early universe, the so-called primordial gravitational wave, is of nanokelvin, we have B modes in our own galaxy, which is of the order of Kelvin. So we have to get rid of all these Kelvin things and we have to isolate the nano Kelvin. So that is the problem of foreground challenge we call. And there are a lot of secondary sources in CMB that can also bias the B mode measurements. So we are all looking forward to get B modes. If we get it, that will be the third Nobel Prize in physics for CMB science, because that is the only way to get the primordial gravitational waves as a measurement. Okay, so this brings me to this slide where I want to show you the current and future CMB telescopes. So Atacama Cosmology Telescope is a microwave telescope that recently completed its survey. So speciality about microwave telescopes in ground is that we have to set it up in the very dry place, because microwave is always having problem with water vapor, because water vapor can absorb microwave signals. So we set up telescopes in the ground if the place is dry. So we have telescopes either in Atacama desert, or we have telescopes in South Pole. Okay, because South Pole is also a very dry place. Also, there are many other factors. It's not just a water vapor. We have to think of the travel and other radio interference and many other factors. So Atacama Cosmology Telescope is what I'm showing here. Then we have a South Pole Telescope, which is in this. And then Lightbird is a future mission, which is like specifically focused for detecting B modes. So the B in Lightbird stands for B mode. So this is a Japanese mission. Then comes Simons Observatory. Simons Observatory is it's one of the best current data that we have. I mean, so Simons Observatory started observations very recently, a few months back. So it is kind of a successor of Atacama Cosmology Telescope in the sense that it is set up in the same Chilean Atacama site. But compared to Atacama Cosmology Telescope, we have very high resolution and high sensitivity with more than one detector. So in Atacama Cosmology Telescope, we'll have just one telescope. Here there will be an array of telescopes. Then comes CMB-S4. CMB-S4 is a future-based future telescope. So this will be like a stage 4 telescopes. So CMB telescopes can be classified into stage 1, stage 2, stage 3, etc. in terms of the number of detectors, sensitivity, etc. So Simons Observatory Act, they are all come under stage 2 and stage 3. But stage 4 will be having a lot and lot of detectors. So if you have more and more detectors, then the sensitivity is going to increase and the way we make the measurement is going to be more and more precise. So CMB-S4 will be a stage 4 experiment having around 5 lakh detectors. So, and that is going to measure very precise, that's going to give us very precise measurement of all these signals that we are looking for, including the B modes. Okay, so apart from B mode search, there are very exciting questions these experiments are trying to address. So given the time constraints, I did not explain many of these things. So briefly, CMB lensing. CMB lensing is the gravitational lensing happening to the CMB when the CMB travels from the last scattering surface towards us. So it's able to map the dark matter distribution. Also, I told you about the Gaussian distributed inflationary perturbations, but some of the inflationary model predict that there could be some deviation from primordial non-Gaussian, I mean, some deviation from Gaussian distribution, which we call as the primordial non-Gaussianity. Also, there are a lot of particle physics interest, light relic particles, neutrino mass, everything, and many others. And we can observe Sunyaev-Zelkovich effect to study the cluster physics. I can explain all these things if you have questions later. Also, some millimeter transient studies we can do. People try to look for the spectral deviations in the black body spectra. So many things are there. So it's opening up. We are not closing things, we are actually opening things. So that brings me to the last slide. So to summarize, the CMB has unveiled the secrets of the universe, and it continues to offer new insights into fundamental physics and cosmic evolution. Thank you.
Thank you, Fazlu. I hope I'm audible.
Yeah, I can hear.
Okay. Okay. Now we are open for discussions. So we do have a question in the chat box. I'll read
Okay,
it out for you.
sure.
What exactly is the fluctuation that is in the CMB, which lambda CDM does not explain?
Okay. Yeah, that's a nice question. I didn't get enough time to explain that, but I'm happy that it came in a question. Okay, so where should I go? Yeah. So the question can be translated into what are the problems of Lambda-CDM that is having mismatch with the CMB observations. So first thing is that we know that there is a problem of, we call it homogeneity. So the homogeneity idea is that uh, as per the rate of expansion that Lambda-CDM explains, the universe should be causal at the time of recombination only for 1 degree patch in the sky. So I'll go to this image. Yeah, this image. So we know that this image is representing a homogeneous CMB temperature at the very large scale. Okay, but if you are just following lambda CDM, the homogeneity scale will only be 1 degree patch in the sky, because there is always a causal horizon, because there is always a finite speed of light and the universe has a finite time of beginning. So the idea of particle horizon, which we call, is that if there is a photon coming starting to travel since the time of Big Bang to some particular time, then that will actually gives a horizon, and that horizon will be the maximum distance to which the information can travel. Okay, so that is the boundary to which maximum information can travel. So that will determine the maximum scale of homogeneity if we are following the lambda CDM. And that will correspond to just 1 degree. But we are not finding the homogeneity just for 1 degree. We are finding that the entire universe is homogeneous. So this is one of the discrepancy. Another one was that if you are just following lambda CDM, we are finding the lambda CDM is saying that the universe is flat. I mean, the observations are saying that the universe is flat. Lambda CDM, if you're just following, we should find that if the universe is flat right now, it has to flat all the time, which is kind of weird in the sense that there is no reason to think that the topology of the universe is flat. So these are the some of the problems. And of course, the origin of the density fluctuations, which lambda CDM itself cannot explain, and we need some other theory. So I hope I answers the question.
Okay, thank you, Fazla. We have another question from Devika. Is the CMB currently in the microwave length region or the radio wave length region, approximately 7 centimeter?
Yeah. So yeah, then that's a good question again. So yeah, so I told you here this is 7 centimeter. So this 7 centimeter will correspond to the Rayleigh Jeans regime of the blackbody spectra. So which will be somewhere around it is one, so yeah, somewhere around this region. Okay, so the when we are making the measurement will be from, let's say, maybe some 50 gigahertz or maybe 30 gigahertz, 40 gigahertz to some 250 gigahertz or 300 gigahertz. So we make measurement at every point. Then only we will get the spectra. Okay. So this is only needed. If we just need one CMB point, we can always get, or we can always measure at this point, which will be in the Rayleigh Jeans limit and which will be radio. But then the problem is that in those regimes, we have contaminations from other signals. We have synchrotron radiation and we have free radiation from our galaxy, which can cause problem. So we have some clean window where we can do CMB measurements. So that is in the microwave. So yeah.
Maybe I have another question added to
Yeah.
that.
Yeah.
So during the emission, it was not microwave.
Oh, are you
Uh,
asking about that? Okay, so when it was emitted, it was 1,000 times larger than the wavelength right now, right? So if it is 7 centimeter right now, then it will be like maybe some 700 micrometer, something like that. That will be
so
near IR.
so the expansion caused
Yes.
the
Yeah.
photons to
Yeah. Yeah. So
go
so it is
inside. So
just close to visible, but not visible. Just close
oh,
to visible, then it became IR. Yeah.
okay, we have another question. Does the gravitational lensing affect the CMB observations?
Yes. So that was the last slide I have. Unfortunately, I didn't keep any backup slide. So what happens is when the CMB travels from this slide, yeah. So CMB is starting to travel from here, and we are here. So it is traveling towards us. So there are a lot of galaxies here. Dark matter is there. Dark matter has gravitational potential, and the CMB photons has to undergo, I mean, gravitational lensing because of that. And the good thing is that studying this gravitational lensing, we can map the distribution of dark matter in the universe and the entire gravitational potential of the universe since the time of CMB emission toward till us, till our time. So that's actually a good thing. But again, there are problems for B modes in the sense that lensing can create unwanted spurious B mode signals because of the lensing effect. So it's basically, I mean, it's good and bad. So yeah.
Okay. So if anyone has any question, they are also free to unmute themselves and ask, or you can also write that in the chat box. So let us give that a moment. So I have another naive question.
Yeah.
So we have this Big Bang and then the inflation and then the other domination eras. So during the inflation itself, do we still say that the universe is dense?
Uh, Okay, yeah, nice question again. Yeah, so what happens is at the time of inflation, inflation is actually pushing everything, right? So inflation is making universe cool. Okay, so the rapid expansion, you can think like, okay, it has made it very, very, very cold. Then we have a phase where universe is dense and hot. So there is a transition from this very cold. At the last moment of inflation, you can think like it's very cold. Then we have the immediate time when the radiation epoch starts. So there is a process in between, which we call as reheating. So reheating is what heats up the system and gives the radiation dominated era, which is very hot. Okay, so and then the idea of reheating is that whatever particle which was driving inflation, which we can call as an inflaton field. So this inflaton field is converting, it's getting converted into the standard model particles. So this is the process of reheating, and that is increasing the temperature of the universe. So that's how it is. So that's a phase transition. So it's a discontinuous process.
Okay, thank you.
Yeah.
So we do have other few questions here. I hope you have time
Yeah, please,
for
please. Yeah.
another.
I would love
Okay,
to.
so another question is how does the SZ effect change the observational data of CMP?
Nice. I'm very glad that you're touching all the points that I'm not, I didn't get time to talk about. So, Sunya's effect is a very interesting effect in the sense that I have to go back here again. So, yeah. So here we have galaxies, galaxy clusters. Okay. So now in galaxies and galaxy clusters, so what is there? So there are stars and galaxies, and there is some region called IgM. IgM is the intergalactic medium. So intergalactic medium has fast moving electron. They are very hot. X-rays are emitted from there. They're very hot and they have fast moving electrons. So these fast moving electrons, they have very high energy. So CMB, I mean, when we compare the entire electromagnetic spectra, CMB is a low energy signal, right? So when the CMB comes, so CMB is coming from here and here, and whatever IgM that is here. So when CMB comes from here and hits these electrons, fast moving electrons, inverse Compton scattering happens. So inverse Compton scattering happens and CMB actually gets more energy from these electrons. Okay, so this is a secondary process that's happening. So initially we told CMB is a black body spectra, but this black body spectra will get distorted because of this inverse scattering process. So AZ is this effect. So it is named for Sunyaev and Zelovich, Rashi Sunyaev and Zelovich. So AZ effect is the inverse Compton scattering effect, and that will change the black body nature of the, that will, you can think like that will change the temperature of the 2.725 temperature that we measured. Some slight distortion will happen. So in that way, I mean, again, this is a good thing in the sense that that will help us to track the physics of clusters. We can understand the electron distribution. So it's like whatever happens between CMB and us, that's good in some way, but that's not good in some other way, because SZ can contaminate our primordial signal. But using SZ, we can study the clusters. So I hope I answers the question.
Okay, another question. Is there any evidence for anisotropy or dipole in CMB?
Okay, again, very
This
nice question.
question is from Hassan Basri.
Okay. Yeah. So there's a very interesting discussion these days that definitely there is a dipole in the CMB measurement. So that is coming because we are all moving towards some particular direction. So the dipole can be decomposed into many dipoles. So if the telescope is in the ground, then Earth is moving with respect to Sun. So that effect has to be there. And even if it is a space-based telescope, so the space-based telescope will be rotating around Earth, and then the system, the telescope or the satellite and the Earth is moving around the Sun. So that is one source of dipole. So that is something that we know very well. So that's what we call as the orbital dipole, because we know what is the speed with which we are rotating, right? Second thing is that the Sun is moving, or the entire solar system is moving in the galaxy. Now the galaxy is moving with respect to, so all the contributions will come. So now when we have the actual measurement, we will see a very large dipole. So this large dipole has to be coming from all the motions that we have with respect to the so-called CMB rest frame. You can think of CMB as a frame, rest frame, and we are all moving with respect to that rest frame. So with respect to that rest frame, we have some motion, and that will be seen as a dipole in the data. So that dipole will be of the order of some millikelvin. So the monopole is roughly Kelvin. Dipole, because of all this motion, is millikelvin, and then we have anisotropies, which is in microkelvin. Apart from that, people are discussing about some anisotropies in the universe, not with respect to CMB, or not with respect to the CMB data, but with respect to some other observations, for example, quasar observations, or maybe some radio point source observations. Using all these things, people are finding some intrinsic dipole in the CMB, and they are questioning the assumption of homogeneity and isotropy. So that's a completely different research topic, and that's becoming more and more active and more dynamic these days. So I'm just mentioning that. But in the case of CMB, we only have this dipole coming from that. So yeah,
Uh, okay, we have one more question from Sharat.
yeah.
What kind of interaction is responsible for particle production from the inflaton field, from where the extra energy is generated to again heat up the universe?
Okay, yeah. So, since I'm not an inflation person, I don't have a proper answer to that. So, I just want to say something. So, you can read about parametric resonance. So, that is some process. I mean, maybe if Ratul is there, Ratul can answer. I don't know, because I'm not an expert on inflation. So, unfortunately, yeah. So, maybe you can read about parametric resonance. That's the only thing which I know a term. Again, I'm not an expert in those things. So, yeah.
Okay. Do we have any other questions? If anyone wants to ask directly, we can also unmute and ask. Okay, we have another question from Vignesh Manoj again. When we are talking about inflation, what model are we discussing specifically?
Okay. Yeah, so when we talk about inflation, there are hundreds of models for inflation. And so the idea is that we need to constrain models based on the predictions of different models. So whatever I have talked so far, and from an observation point of view, we don't specifically talk about one particular model. We try to, I mean, once we have data, we try to rule out some of the models, and we try to say, okay, some of the models are working fine or fitting better with the data. So that's how it works. So yeah.
Okay, so yes, thank you. Uh, I hope there is no more question because Fazlu is from a different time zone and I think he needs to get his good night's sleep right now. So
That's
thank you,
okay.
Fazlu, once again, and thank you
It's
very
my
much.
pleasure.
And also for thanks to the audience for asking these wonderful questions.
Yeah, I loved
We
all
had
of them.
almost 35 participants
Oh, that's
from
great.
various places. So thank you very much. So we'll be uploading this recording on YouTube. And Fazlu, if you're kind enough, if you could share the slides, we can also
Yeah,
upload
sure.
them.
I would
Otherwise,
love to.
it's
Yeah. Yeah, I can
okay.
share that with you.
Okay. So
Yeah.
thank you again. Thank you,
Yeah.
Vaslu.
Thanks
Thank
again.
you
Okay.
again for all the adventures for the CMB, and I do hope that we resolve some cosmic tension in the
Yeah, we
upcoming
hope we'll
future
get the
with
B mode
CMB itself.
soon. Yeah.
Yeah. Okay. Okay. So
Okay.
thank you, Vaslu. Thank you again. People are thanking you on the chat box. So
Okay. Thank you so much
thanks.
for all the questions and bye. Have a good day.
Okay. Thank you everyone for joining KTPI again, and we'll be back with another talk in the future. And until then, this is Manoj signing. Bye.